Hi everybody, and welcome back to Digital Integrated Circuits. I'm Professor Adam Teman of the EnICS labs at Bar-Ilan University, and today we'll be going over the Kahoot for Lecture 8, SRAM. This Kahoot has 8 questions, and the first one is, how many bits are in a memory with 1024 words of 64 bits? Is it 2 to the 12 bytes, 64 kilobytes, 2 to the power of 16 bits, or 1 megabit? I'll give you a moment to think about that. The answer is going to be 2 to the 16 bits. So let's go over the memory organization again. And what we'll see is that basically we have a memory that with the letters that I decided to use to kind of make it maybe clearer is that we call the number of words in a memory W. And words have a certain number of bits, something like 32 bits, 64 bits. Sometimes we discuss in bytes, which are 8 bits. So that is C bits. So a total number of bits in the memory is W times C bits. So if we said that we have 1024 words, means that W equals 1024, and we have 64-bit words, that means C equals 64. We have a total number of W times C that equals 64 times 1024. But we usually work in powers of 2, so that means 1000 is 10 is 2 to the power of 10, so 2 to the power of 10 is 1024, and 64 is going to be 2 to the power of 6. Okay, so that means we have 2 to the power of 16 bits in total, and that was the answer. Our second question, we have a puzzle. Organize the types of memories from fastest or most expensive at the top to highest density or cheapest at the bottom. So fastest, most expensive. I will say that has to be the registers that we discussed there out of standard logic and so forth. The next fastest is the embedded memories, the SRAM. But it's also the second most expensive because from about 30 transistors it goes down to 6, but that's still 6 transistors. The next fastest is going to be DRAM, which is off-chip and 1 transistor, and the cheapest really is going to be a magnetic hard disk. To answer that, let's look at the memory hierarchy of a personal computer. So really at the top we have our CPU or our computational unit, whatever it is, and closest to the top, this like tight pyramid, we have the fastest, the closest to the actual computational unit, which means we get the highest speed. But it usually means that, unfortunately, the cost per bit also becomes much higher. Okay, and therefore we have, this is much shorter over here, which means we have a much lower density. And the first thing up here are going to be the registers, the flip-flops. I guess it could be latches or whatever, but they're really in pipe inside the data path, and that's going to be the most costly type of a memory that we have. Usually the first level of a cache or the closest memory, the tightly coupled memories and so forth, they will be made with SRAM, which is an embedded memory, an on-chip type of a memory, which we have been learning about in this lecture over here. So we have 1, maybe more, maybe 2, maybe 3 levels of cache or some other scratchpad memory or some type of memory that is on chip that we use that is made with SRAM. And again, SRAM is going to be 6 transistors per bit, and so it's more costly than it's more costly than other things, but it's less costly than the registers, which are really a few dozen transistors per bit. But it's also, and it's going to be slower. It's not going to be in pipe. We have to actually access the whole array at once. We can't access a particular bit in pipe and so forth. But it's still very fast and very high bandwidth to it and so forth. When we go deeper down than that, we usually have to go off-chip. And going off-chip is over here when we reach main memory. And main memory is, up till today, done with DRAM, dynamic RAM, which we'll learn about in a few weeks. When we discuss other types of memory. But we're able to use a special process to make a memory bit cell that has 1 transistor and 1 big capacitor, and it's a much slower because we have to go off chip, and the way it's made is much slower than SRAM. But since we have only one transistor per bit, it becomes much cheaper than SRAM. We can get those higher densities to get DIMMs with several gigabytes of memory on one type of a chip. Okay, and then once we want to go to even higher densities, we're willing to lower the speed and take many more cycles to actually access that. And then we'll go to secondary storage, which could be a hard disk traditionally, but in recent years it becomes either flash or an SSD, which is also based on flash, which is faster. And even there might be some sort of like even lower level, which is going to be remote secondary storage, which could be through the web or something like that, or just these types of archival tapes and so forth that might store some things. So that's the memory hierarchy of a personal computer. And coming back to our puzzle, indeed, the top one is the registers. Those are the fastest and the most expensive. Then SRAM is the embedded memory. It's the next level down. DRAM is already going off chip, so that makes it a lot slower, but we can make very cheap bit cells. And going much farther, and this can take even millions of cycles for just to access it, we get to the hard disk, which is really cheap, but it's also very slow. For our third question, what is the read constraint of an SRAM cell? The pull-up device must be weaker than the pull-down device. The pull-down device must be stronger than the access device. The access device must be stronger than the pull-up device, or the pull-down device must be weaker than the access device. And the answer to this one is that the pull-down device must be stronger than the access device. So let's go back to our slides, and we saw that the SRAM operation in read, and it doesn't really matter if we take a 0-1 or a 1-0 state inside the SRAM bit cell, because the 60 SRAM cell is perfectly symmetric. So I decided here to take, Q equals 1 over here, QB equals 0 over here. What we're going to do is we're going to pre-charge the bit lines to VDD, and that's going to be on the parasitic capacitance of the bit line and bit line bar. And then we're going to turn on the word line, so we're going to pull this and this up to VDD. And so we start with this situation where we have VDD here, and over here VDD, and over here VDD. And we can draw basically between the two sides, we can draw a schematic that shows us what's going on. And so with Q and Q bar as our output, well, if we look at Q, we're pulling up to VDD over here, and it's not actually trying to fight with the one that's over here, but when we have VDD over here, we're trying to actually pull up this type of a situation over here. And we take the schematic and it comes out, as we saw in the class, something like this, which is just a type of an NMOS inverter that is pulling down its output to the lowest point possible, which we would call the VOL or something like that. And it's going to be some sort of a delta V. It's going to be larger than 0. And we don't want it to be too high, because if the access transistor is much stronger than the pull down transistor and our delta V becomes really high, so if M5 is the strong one, we're going to be trying to pull up to VDD, and then we may actually flip the other inverter, and everything will basically write the situation of a 1 to this side of the cell, and that's not what we want to do, because we're reading from the cell. We do not want to destroy the data inside. We just want to read out what is there. So we want delta V to be as low as possible, and we achieve that by having M4 being stronger than M5, or the pull down transistor be stronger than the access transistor, and that shows us our cell ratio over here. So again, back to that, the answer is that the pull-down device must be stronger than the access device. That is what we call our read constraint of the SRAM cell. Question number 4. If we talked about the read constraint, now what is the write constraint of the SRAM cell? Is it that the pull-up device must be weaker than the access device? The pull-down device must be stronger than the access device? The access device must be weaker than the pull-up device? Or the pull-down device must be weaker than the access device? And what we want is that the pull-up device must be weaker than the access device. So again, going back to the slides that showed the state of our write constraint, in this case, as opposed to the read constraint, we put opposite levels on the two bit lines. And so what we're going to do here is we're just assuming for right now that we have a 0 over here and a 1 over here, but it doesn't really matter for our analysis. What we are assuming here is that we're writing a 1 into the cell. So we put VDD on the bit line and we put 0 on the bit line bar. But we already saw before that on this side what we get is exactly the situation we had for the read constraint, and that's that NMOS type of inverter, and we already made sure that Q0 will not be pulled up over some very small delta V, the VOL min of that NMOS type inverter. And so we cannot actually write into this side of the cell. We can only write through the side that we pull down to 0. So in this case, when we draw the schematic that comes out of it, we get this situation over here where we have a pseudo NMOS inverter. And a pseudo NMOS inverter again has this VOL, you know, this the low output of it, where we have the weak pull up of the PMOS device pulling against the strong pull down of the NMOS device, and we want the strong pull down to win, so we have a 0 level, because what we want to do is we want to write this 0 into the cell. So to have VOL min as low as possible, or at least lower than whatever will really flip the sides of this cross-coupled inverter pair, what we want to have is VOL min be as low as possible. So M5 has to be stronger than M6, or have a strong access device and a weak pull-up device. So our answer again to what is the right constraint is that the pull-up device must be weaker than the access device. We want a really weak pull-up device. Question number 5. What is shown in the following figure? Is it 2 SRAM cells? Kind of looks like it. Is it a dual-ported SRAM cell? Possibly. Is it an SRAM cell with reset? Well, I don't see any reset in these signals here. Or is it a dynamic SRAM cell? I don't think we discussed that at all. So I think it's going to be a dual-ported SRAM cell. Let's go back and discuss that. So what we discussed with a 6T cell is what we call a single-ported memory cell. We can only access one address at a time, one row of the memory, for either read or write operation during a single cycle. But there are many applications that need to have multiple accesses to the same array, and for that we need a multi-ported memory. And so there are two types of of memories with 2 ports that are very commonly shown. There is this dual-ported SRAM, which we can call 2RW, because it can support 2 read or write operations at any given time. Or we have a 2-ported SRAM, which is 1 read, 1 write, because it can support 1 read and 1 write simultaneously, but not not 2 reads or 2 writes at the same time. So the dual-ported SRAM, which is what I showed in the picture before, is basically the same thing as a regular 6T. So as you can see here, we have the basic structure of the 6T that we're used to. But what we do is we add another pair of access transistors. Okay, and by adding another pair of access transistors and another well, I took the word line 1, but another word line and another pair of bit lines, what we can do is we can have one row. Remember that our array is going to be, you know, a 2-dimensional type of a thing, and we can take a row over here and assert if this is going to be word line 1, for example, you know, for port 1, we can turn on this row, okay? And then through the bit line and bit line bar that come out, the bit line and bit line bar 1, we can read out or write to this cell itself. But if we turn word line 2, let's say over here on, over here, then we can read out, you know, through bit line 2 and bit line bar 2, we can read out, you know, these guys, or to these guys. So we can simultaneously read and write, read and or write to 2 different rows during the same cycle, as long as word line 1 and word line 2 are 2 different addresses. How do we make sure they're different addresses? We can either make a circuit that will make sure of this, or we can do it architecturally outside the die. The other option is the 2-ported SRAM, which is a similar type of a thing. Instead of adding, you know, a whole pair of word lines and bit lines, it actually only adds this kind of decoupled readout port. So what we have here is the standard 6T cell, and then we tap one of the either Q or Q bar junctions over here, and we take it to another readout port. So this port is similar to this guy without the pull-up, because we're not writing through it, we're just reading from it. So if now we have a 0 over here, this is going to be off. If we have a 1 over here, this is going to be on. And then when we take the RWL line over here and we assert it, we bring it up to 1, then we can discharge RBL bar, this RBL bar that we have over here. So that enables us to do a read from this row and a read or a write from the row that selects this, but usually we separate it to have writing through this line and reading through this address over here. So that is multi-ported SRAMs. We can of course expand this to more ports and so forth, but it first of all makes the bit cells much bigger, and it makes us have a lot more peripherals, and second of all, it loses all kinds of problems with stability, and it's not very commonly found. So usually memory compilers will have up to 2 ports or 1 read, 1 write port, and not many more. Our 6th question, what is shown in the following figure? Is this hold static noise margin, SNM? Is it read static noise margin, RSNM? Is it write static noise margin, WSNM? Or is it dynamic noise margin, DNM? And of course, if you watch the lecture, the answer is read static noise margin. Let's go over the different types of static noise margin we have. So if we just take our 2 cross-coupled inverters and separate them and put the Q and Q bar onto the same axis, we get the VTC of the feed-forward path, the regular VTC of an inverter, and we get the flipped VTC of the feedback path, where this is the V in and this is the V out, where it would be from something like Q bar to Q. Okay, so when we put these on the same plot, we get what we call the butterfly curve, and we find the largest square that we can put into the butterfly, and the length of the side of this square is going to be the SNM that we have during hold. But this assumes that, as you see, there are no access transistors because they are cut off. So that is for hold, and that is hold static noise margin. On the other hand, when we go and we enable the word lines and we pre-charge to VDD, we get these 2 NMOS type inverters as we saw before, and what they're going to do is they're going to have this some sort of a VOL over here. It's going to be over here, and a VOL over here, that are not going to allow our VTC to get all the way to 0. And so it's still going to be symmetric, and so it's going to take these lobes and make them smaller and give us a smaller square over here, and that's going to be a read static noise margin. So that is what we achieve under read. On the other hand, with write, we get again this other type of a parallel scheme over here, as we saw before. But with write, what we want to do is we want to disrupt the bistability of the cell. So we do not want to have our cell have these 2 states, either a 1 state or a 0 state. We want to ensure that it gets only to the 1 state that we're writing to. So we want to bring this to this state. We don't want to allow it to come into some other state. So we want to break the bistability. How do we break the bistability? We pull this blue and this red curve away from each other, and we get something like this. So this is the inverter, that is similar to this, which is in this, type of read situation where we had VDD on the bit line, and we have this weird thing which is a non-digital, not an inverter or anything, on the right line, and we need to ensure that they never touch each other, because if they do touch each other, then we will have another stable point, or actually a stable and a metastable point. So the right SNM is the distance, the side of the square that we can put inside between these 2 that they never touch each other. So that's going to be the right SNM. This schematic enable. Schematic over here has these transformations, transformation 1 and transformation 2. It gets a DC sweep at the input. It has these 2 6T cells over here. One of them gets Q to QB, the other one gets Q to QB over here, but they're actually connected differently between Q and QB on the transformations. And is it measuring hold SNM, read SNM, write SNM, or SRAM leakage power? And we look at here and we see that there's ground and VDD. That means it's write SNM. And did I push it on time? I did. Okay, so let's go back to the slides and see what I'm talking about. As we saw, the way that we're going to really nicely measure the static noise margin is we're going to take our butterfly curves and we're going to rotate them with a change of coordinates. Okay, and doing that, then we can take the feed forward inverter and the feedback inverter and just subtract them from each other, and we will get the sizes of all of these diagonals that fit into the lobes of the butterfly curve, and we get this nice type of thing over here, and we can choose what the maximum is very easily. So we get this SNM is the minimum of the maximum sides of the curve. Okay, how do we do this transformation? We take the transformation matrix, we get this equation over here that V equals U plus square root of 2, the feed forward path as 1 over square root of U plus 1 over square root of V, and that's actually this circuit over here. So we have U as our input over here, then we have these dependent voltage sources, which this one is minus 1 over square root of U, and this one is 1 over square root of V2. We have V out over here, and we have V2 over here, and V2 is going to be now square root of 2 times V out minus U, where this is the feed forward path that goes through. And the same thing is for the other rotation, where this one we rotated 45 degrees over that way, and this one we had to flip and rotate. Okay, and that's this transformation over here. And if we apply those two things, we can plot both of the butterfly curves, get this plot, do the subtraction, and so forth. Okay, so how do we do that? We actually build, schematics of the 60 cells. We build schematics of the transformations, and then we can just do the connection. So that was for hold SNM. For read and for write SNM, all we actually have to do is change the biasing of the bit lines. So for read, we put both of the bit line and bit line bar at VDD, and for write, we put one at ground and one at VDD. It should be pretty much symmetric, so we don't necessarily have to do this on both sides, but be due to process variation and so forth, or if you're using a non-symmetric bit cell, then you would have to do it for both writing a 1 and writing a 0 to the cell. What we saw in the Kahoot picture was, as we can see kind of over here, we have ground and VDD on the picture. That means we're checking a write 0 situation, so we're measuring write SNM with this schematic. For our last question today, what is the difference between initial condition and node set? Node set is used for transient, and initial condition is used for DC simulations. Node set is used for DC, and initial condition is used for transient simulations. Node set is applied to nets, and initial condition is applied to capacitors. Transient simulations don't take initial conditions into account. Well, the answer is going to be this blue one. Just as a final reminder over that, SPICE supports two types of conversions aids. One is called node sets. Node set helps SPICE convert by providing it with initial guess. I actually did a lecture on how SPICE works behind the scenes, and I uploaded it to my website or to my YouTube channel, so you can look at that and understand much better what node sets exactly do. But when we do any type of analysis basically in SPICE, we do this type of Newton-Raphson method to converge on an operating point, and it basically guesses and fixes the solution to our DC situation of our circuit. And so the initial guess, which is a node set, will help us converge faster, but also for the case that we have multiple stable points, such as the SRAM cell, where we have two stable points, the two real stable points and the metastable point, putting in a node set will push us towards one of the stability points versus the others, so we can check what the situation is when we have a we can check the DC conditions when we have a 1 or a 0 inside the cell, or check what it is when it's metastable. Unfortunately, the basic thing, if you don't use node sets on such a metastable circuit, is often that it will settle at the metastable point, which is exactly the point that is basically non-physical and you'll never meet, so you don't want it. But since due to the structure of the cell, often it will actually settle unfortunately at the metastable point and give you wrong answers. So you should use node sets by giving some sort of a bias to your Q and Q bar when you're doing an SRAM simulation, and node sets are in general very useful for getting faster convergence. On the other hand, when we do transient simulations, we have initial conditions. That is basically the charge that is stored in the capacitor, the current that is going through an inductor at time 0, or setting whatever the voltage at a node is, or the current through one of the components is at time 0. So we can set that with initial conditions. Transient simulations do not take into account node sets, and node set and DC simulations are the initial conditions are irrelevant for them. So back to our answers over here. Node sets are used for DC, and initial conditions are used for transient simulation. That is the accurate answer. I also wrote here that node set is applied to nets and initial conditions to capacitors. Well, the initial conditions are on capacitors, but node sets and node sets are applied to nets, but initial conditions are also applied to inductors, and they can be applied to nets as well as voltages, so that's not an accurate answer. And transient simulations don't take initial conditions into account. Well, the exact opposite is true. Transient simulations only take initial conditions into account. Okay, so basically that was our Kahoot for this time, and as always, any questions you can leave on my YouTube channel.